precision measurement solutions and techniques that we can use for characterizing and evaluating power electronics in this changing ecosystem. Let's go ahead and get started. So we're going to start off by wading in and talking about how power electronics are changing in the current market, the challenges we face, converting that power, using it efficiently, some new technology and some technology that's coming to bear against these problems and challenges, including wide band gap semiconductors. We're going to talk about some test and measurement specifications that on certain instruments are becoming more important and worth consideration in some of these challenging measurements. And we're going to talk about some key characterization tests and test techniques that we use to attack some of these challenging areas, including some double pulse testing, emissions and harmonics, power analysis and ripple measurements, efficiency, Bode plot, and load step response. Let's go ahead and jump in. So as we all know, power requirements continue to grow across a number of industries. Some of this is led by automotive, aerospace, IoT work, growing data centers and telecommunications infrastructure, as well as renewable energy and energy conversion infrastructure. All these require more and more power electronics work at higher voltages and more efficiency. Some of the key drivers that continue to push these boundaries forward include electrification of transportation, so obviously the move to electronic infrastructure for car charging, that power demand from data centers, portability of miniaturization of battery technology and power technology on a number of devices, and of course the need for a response to climate change and environmental protection from both the manufacturing process, recycling, and the use of these devices. All that really leads to energy efficiency and improvements in energy efficiency being a critical aspect, a critical challenge. One of the things that drives that need for efficiency is essentially our power conversion system and how we distribute power nationally and around the world. So there's, it's estimated that we have about 5% distribution losses in the U.S. just from moving that power around from sort of that centralized impact of power generation, whether that's an environmental impact or just a regional impact. You also have moving that power around, storing it in different areas, localized storage losses and power conversion issues lead to increased losses. So how do we get that power where it needs to be when we need it? How do we store it efficiently? And how do we use it? And that's all about these power conversion techniques and electronics that we're continuing to use today. And so, kind of a brief overview of power conversion types. Obviously, most of, or at least a lot of what we do is taking that AC power distribution system and moving it into our DC devices. But there's also DC to DC, DC to AC, and AC power conversion types. If we go one level below this, we can look a little more detailed at some of the challenges we face on a type-by-type basis. And efficiency losses are one of the most important here because as we have, at the highest level, efficiency of conversion is absolutely a critical element of these systems. So we have kind of use efficiency at the top level. We have switching losses. As we see here, the sort of the dynamic switching losses of these conversion techniques leads to heat and immediately loss in efficiency at that time. You also, from these as a byproduct of switching speeds. You have increased issues with EMI, noise, and harmonics. And lastly, you have a power factor correction losses that can be a concern on some systems as well. But we're going to spend a lot of time today talking about this, this switching system and how these switching losses, how we can measure and characterize them, and how they affect overall measurements and our overall efficiency. So one of the solutions that's being worked on technologically and has been for many years in this industry is wide bandgap semiconductors. Things like silicon carbide, gallium nitride. What these technologies allow us to do is really push efficiency in these environments. So we increase the speed, the switching speed of these devices. We're able to do it with lower switching losses. That keeps the systems cooler. And that also, we're able to make them smaller as well because of higher power density. So wherever we need that power, being able to use it more efficiently, store it more efficiently, and in smaller, cooler packages is always a benefit to the industry it's being used in. Now, depending upon how you select the technology in play here, you have you get a little bit of a different advantage, right? So when we're talking about now, characterizing the efficiency here and making measurements on this power equipment, we have some devices that allow us to use faster rise times and faster switching speeds. They might have a higher current slew rate or a higher voltage slew rate, right? So how this affects us is with the type of technology that we're using, and as we're selecting technology for our power applications, we have to be careful with bandwidth for these voltage and current measurements. We have to be careful now about EMI and EMC emissions, radiated and conducted emissions issues that come into play in these systems. We have to be aware of our dynamic range. We have to be aware of common mode rejection, especially as we get into higher voltage systems, and how we probe, how we connect, how we make these measurements becomes more and more critical. Let's look at the first sort of example of this, the first impact, which really is all about bandwidth. So, I think one important question for clarification here is how much bandwidth do we need to make good measurements on the switching speeds, the switching frequency of a power device? Well, here if we talk about sort of a classic power device here that has a switching frequency of 100 kilohertz and has a rise time of about 50 nanoseconds versus a wide bandgap device with the same switching frequency, but because of the technology, it has a much faster rise time. What effect does that really have, right? And we can calculate this. We can calculate the bandwidth needed with this formula here. We typically would use a 0.35 divided by the rise time equals the bandwidth. So the classic device here, you really only need about 7 megahertz of bandwidth to make strong measurements here on the switching device. But with these new higher speed devices, even at the same switching frequency, you're really forced to use. You want to use a much higher bandwidth instrument. Here, the formula equates to about 175 megahertz of bandwidth, just to really start to see the effects of that rise time, right? And so without that, you're missing some of that, some of those effects, and you certainly begin to limit the odd harmonics of that signal, right? So you have that rise time, that sharp rise time is really created by odd harmonics in that fundamental wave that go up increasingly high frequencies. And it's even one step more complicated than this. So as we look closer at that 2 nanosecond rise time signal from our wide band gap device, we need more bandwidth. But what is that? If we do get to that sort of 175 megahertz of bandwidth, what does that really do for us? Well, that still leads to a significant sort of rise time error if you're directly measuring the rise times uh, of that device, because you're still attenuating the odd harmonics considerably. So in the industry here, we would use a formula like this, where really the measured rise time of that signal on an instrument like an oscilloscope is really the combination of the signal's rise time and the probe's rise time in a function like this. So, when we talk about a 500 megahertz scope or a scope and a probe together with 500 megahertz of bandwidth, that should have about a 700 picosecond rise time. So if we combine that, in this formula with our 2 nanosecond rise time, we're still, 3x faster than the signal. But you still see a rise time error of about 11% in that measurement when you directly measure the rise time, because you're lengthening that rise time out because of how you're attenuating the higher frequency odd harmonics. So we would use a rule here, what we call the 5x rule for bandwidth, which is really about limiting your bandwidth, your rise time error, to less than 5%. So we would say if you need to measure rise time with 5% accuracy on a high-speed signal like this, you would need 5x the bandwidth on the combination of your scope to the probe to the signal tip measurement. So that in this context would be an 875 megahertz scope, giving you about 400 picosecond rise time, and that reduces the error in this case down below 5%. So that's the kind of environment we're in, the kind of measurement accuracy bandwidth in this case we need to start to accurately measure rise times of high frequency signals accurately. All right. So that has other implications as well. So if we look at a slightly different sine wave here, a slightly different square wave, so switching speeds in a little different environment here, down at 16 kilohertz with more of a microsecond rise time, you can see we can calculate sort of the EMI emissions in a particular environment from this sort of signal. But if we then talk about that same signal again with higher rise times, faster rise times, what we end up with is we can see a 10 nanosecond rise time on that signal can lead to 100x increase in harmonic content as we move into those higher numbered harmonics, right? So 20 dB, 100x kind of increase in amplitude for those harmonics that often are the source of radiated and conducted emissions issues as we're making them. So that really becomes the difference there. As you go to high frequency, you get more gap between those. So as you become worried about higher frequency signals, as you become worried about what emissions impact they might have for your other measurements, you have to be careful of those higher speed rise times and higher bandwidth systems that can allow some of those emissions to propagate. So bandwidth obviously is a critical aspect of these types of measurements, like oscilloscopes, measuring with oscilloscope, things like that. But also important to look at the actual resolution of some of these measuring devices. So oscilloscopes today, we really have access to a lot of what we call higher resolution on the vertical axis, higher ADC resolution up to 12-bit and beyond, with a combination of technologies available. And so what this allows us to do is reduce the quantization noise. We also would decrease the actual noise floor of these instruments as we improve their resolution. And that gives us the ability to improve the sensitivity and the accuracy of these measurements in a couple different ways. But fundamentally, the combination of higher bandwidth and higher resolution allows you to make more accurate representations and visualizations of um, you know, rise times and related signals in these power environments. Two quick notes about how this resolution on the front end of our oscilloscopes can really improve your measurement quality. Certainly, I think one that everyone's aware of is obviously the quantization level, or the gap between bits reduces significantly, right? So you have 16x smaller change that you can accurately measure and identify in those signals. But that also leads to a much higher dynamic range within the same set of voltage or power, right? So being able to more accurately see those small signals in the context of larger signals is really super important in power electronics work and the kind of characterization we're going to be doing as we move into some of the measurement challenges here. So to kind of summarize that, high resolution oscilloscopes, looking at these high speed, challenging, wide band gap semiconductor measurements in power electronics allows us to improve the accuracy, gives you better dynamic range. We often see greater channel isolation, so making multiple measurements across multiple channels, we can isolate those more easily with a new high resolution oscilloscope. We can reduce that front end noise, and that allows us to really provide increased signal integrity and greater measurement detail. One additional challenge that we face in a lot of these measurements is common mode rejection ratio. So as we're talking about, especially floating signals up on higher voltage, like in this diagram here, right? We're trying to measure that 15 volt differential voltage, but we're floating on top of a 600 volt common mode measurement. The ability to reject the common mode voltage and the fluctuations on that becomes a significant kind of key piece to how well we can make this measurement and what impacts it might have. So if we dig in a little bit there, the obviously key to making this high side VGS measurement is this is a ground-free measurement. So we have to be able to make that small differential voltage measurement in the presence of a higher common mode voltage that would cause us issues, right? So we have to make a floating measurement with good common mode rejection ratio, and we have the added dimensions of bandwidth with these fast edges on these pulses that we've been talking about. And so we'll note with many of the probes that we talk about here, common mode rejection ratio, the specification is highly dependent on frequency, whether you're talking about scopes or probing for it, really both. As you move up in frequency, you can see the common mode rejection ratios tend to drop, right? And that allows noise and issues with our measurements stemming from those growing and high common mode voltages. And that really looks like a graph sort of like this, right? As we see a faster rise and fall times with these new technologies and faster switching speeds, as we move to 100 megahertz and beyond, right, we see the common mode rejection ratio of our measurement tools gets smaller, which tends to get to less well, right? We want more common mode rejection, and as this heads towards minus 20 dB or towards zero, this is that high voltage signal impacting our measurement directly. So there's a couple ways we can deal with this, right? One is high voltage differential probes. This can allow us to measure these differential voltages. We can do this in the presence of a higher voltage signal with our differential probe. There's some limitations here to bandwidth and high input impedance on these inputs, so you have to be careful of some loading, some errors, but mostly it's about bandwidth limitation and the correct voltage scaling for these probes. Another way to make this measurement is with an isolated input, right? Where you have no direct earth connection, an isolated scope or entire measurement system allows you to make a measurement well, especially at low frequency. As you get up to higher frequencies, this is maybe less available for this sort of measurement. And it's important to note that these are not you're not truly differential, but you tend to be floating the entire measurement system in this case. A more complete solution to this might be something like an optically isolated probe. So here, as we see on the left, right, your classic high voltage differential probes, the common mode rejection ratio tends to go up as a function of frequency, whereas with our optically isolated probes, that tends to flatten out significantly, and you can see the horizontal axis there goes out to 800 megahertz. So you have much higher access to higher frequency with better common mode rejection across the entire frequency band. So looking at our example again, as you move towards 100 megahertz signals, if you only have 18 to 20 dB of common mode rejection at that frequency, you're really adding volts of signal, of noise onto your system. And when you probe it, it can look like those dynamic changes in those dynamic parts of the signal can look like the orange probe in the bottom right there, where you're getting a lot of noise interceding with your signal. You're getting a lot of fluctuations, really from the effects of the differential probe, and you can alleviate a lot that with a probe like an optically isolated probe like this. So as we look at sort of those measurements across multiple channels, right? We know that we have passive probes up to high bandwidth, 500 megahertz, gigahertz, gig and a half, makes those perfectly suitable to the task. You have active probes and active differential probes that are ideal for small voltages. You have high voltage differential probes in the bottom corner there that are really tend to be lower frequency than your active probes, but much more suitable for higher voltage offsets. And then you have the power rail probes and the optically isolated voltage probes that are really great for those common mode rejection type measurements. So let's take a second and talk about this probing and how we do it. So, as we're looking at these high-speed signals, our ringing and resonance becomes an issue as we try to probe these high-power measurements, and we have to be able to find ways to alleviate that ringing and those signals that are really aberrations and not part of our actual signal. So finding better ways to shorten that loop around the probe. What you typically see, like the passive probe on the left on our left here, this ground clip creates a loop area, and we have a lot of current and voltage in the area here that causes us problems. So shortening that ground loop with ground springs, tightening up, making those connections close together, and alleviating that loop area is one great way to really improve your actual visualization of that signal as you probe it directly. Okay, so we've talked a little bit about some of those measurements and probing. Before we head into sort of a handful of test techniques, let's just summarize these kind of measurement challenges that we've walked through, right? So we know we need to make high voltage measurements in some of these areas up to kilovolts. We have to have accuracy. We have to improve our dynamic range, and we have to do that in a context of Measurements where more bandwidth um, uh, is important. Also, where we don't have a lot of access to ground. So finding ways to isolate those measurements, make differential measurements um, um, is important to measurement accuracy, especially when we're talking about high side VGS measurements. We have to be aware of common mode disturbances. We have to be aware of capacitive coupling of channels together as we make multiple measurements. And then we have some additional challenges in the current side, right? How do we access those PCB traces to make those current measurements directly? Current probes will add inductance to these measurements. They're reactive, so we have to be careful how we probe and access those as well. We have just being able to build this probing system in a way that's both repeatable, low noise, accurate, hands-free, and not causing us a lot of additional challenges, as are all important aspects of that proper selection of isolated and differential probes, and compensating and connecting them correctly. All right, let's talk for a minute about double pulse testing. So double pulse testing, what is it? Double pulse testing is a methodology for conducting a test on these semiconductors by pulsing the gate quickly in sequence. So varying the timing and the amplitude of the gate pulses here allows us to learn some intricate details about the high-speed recovery and the different aspects of this of the semiconductor itself and how we select it and put it together. So when we look at that measurement, we can see that we're talking about a sequence of pulses, right, on the gate, and we monitor the drain current and the voltage as well. And what we can see typically a number of measurement artifacts here. So we see spikes at, for instance, the drain voltage spike at time T2 on this chart here. That tends to be a product of stray inductance and the current slew rate of the ID current. We see things like the spike in the current here at the bottom at time T3 as well. That tends to be recovery current of one of the Q1 diodes. So we can alter the timing and speed of these pulses to understand how this whole system is working together and what the most efficient way to operate this device is. So as we go ahead and go into measure that, we want to probe it in this way, right? So we need to probe the gate voltage. That's typically coming off of a pulsar here. In this setup, we're using a waveform generator to set that pulse timing and pulse sequence. Then we're measuring that with a passive probe on the oscilloscope. We want to use a high voltage differential probe to measure the drain source voltage, the voltage across our device, as it can be higher and may need to be floating. And then we need some kind of a current probe or current measurement technique to look at the current coming out of that device as well. In this case, it's a MOSFET that we're testing here. So the ability to look at all these measurements together, and in this case, automate a test to really conduct these pulses and do a pulse study becomes important. So let's look at the several things we can learn about the converter's efficiency using a double pulse test technique here. First and foremost, we can learn a lot about the switching loss of these devices. We can measure turn on and turn off losses. We can measure the direct impact on the efficiency there as well. We can compare devices. For our specific application, we know what kind of drive power-wise we need. So we can look at different technologies and different implementations of the circuit to compare efficiency across a wide set of technologies. Then once we've really settled into the right device and basic setup that we need, we can do further evaluation to really optimize the gate drive, right? So changing how we time and work with those pulses can teach us things about how to reduce losses within those switching losses and that timing events. We can also go ahead and do what's called dead time optimization, which is further tuning that to make sure we're minimizing what's called the body diode conduction for a device like these MOSFETs. So, direct measurements of the dual pulse test allow us to look at the converter's efficiency, select and improve iteratively in our design. Then once we go ahead and select that device and set up our system, now we have some broader characterization techniques a little farther away from the direct device here that we want to make about a more complete system or subsystem for power measurement work. So let's talk about through several of those. We're going to start with power analysis and talk through a couple different techniques. So in this context, power analysis is where we're really looking at a combination of power quality, things like power factor, apparent power, reactive power, phase, and crest. We can make direct measurements of the current harmonics, in this with systems like these up to the 40th harmonics. We can look at inrush current directly. Of course, we can make those switching loss measurements that we were just talking about. We can make slew rate measurements. We can look at ripple and turn on, turn off errors, as well as transient response and overall efficiency. So, this kind of a power analysis setup is really, all these measurements are built into a number of the high resolution oscilloscopes and a number of SIGLENT oscilloscopes there. So usually it's an option, and you can add that together with probing to go ahead and sort of make direct power measurements and do all this analysis together in one place. Specifically about harmonics, right? When you're often talk about sort of a single phase switch mode power supply. Those harmonics, current harmonics especially, become super important, right? So they lead to a lot of emissions issues and some other control issues. So you have to. It's important to be able to measure out to high number harmonics, directly up to 40 harmonics as well, is what we're able to do there. So you can see that the odd harmonics continue to have important current and relatively high current levels out to the high harmonic level, and so you have to be aware of that, and that's an important analysis toolkit and analysis methodology that you need high bandwidth current measurements in some cases to do. We can also build up systems with different instrumentation here to go ahead and directly automate sort of efficiency measurements. And there's obviously a ton of ways to do this. One test system that we've put together here and made some programming and application notes about is a system like this. It combines power supplies, electronic loads, and multimeters in a system to go ahead and directly measure that sort of efficiency of whatever device is in between there. As we deliver power, we're able to measure the conversion efficiency directly. So, combining tools like that, benchtop test equipment for accurate, reliable efficiency measurements is certainly doable, programmable, and easy to automate when done correctly in this type of an environment. A couple other measurement techniques that I wanted to highlight here as we get towards the end is one being Bodie plot measurements. So number of SIGLENT oscilloscopes can work with a function generator, a little module like that one, or a standalone function generator to conduct what we would call sort of a Bodie plot or Bodie plot survey. Right? This is measuring gain and phase changes across a device under test over frequency. So typically sweeping frequency in a decade manner with a function generator and making the differential phase and amplitude measurements. And this is important for these kind of power electronics because you can use this to analyze the feedback loop and look at the stabilization of that system, right? So you can make that you can get to a phase and a gain margin measurement directly as you kind of optimize and build around that system. So the stability of that feedback loop in the context of frequency is another important tool to sort of optimize your final setup in this system. And then, again, once we've gone ahead and done that, one of the other tests we want to do is our load step response. So here we can use an electronic load to step the demands on our power device, and we can monitor the voltage drop, overshoot, monitor the ringing, and then from here we can decide, okay, do we need to increase the phase margin? Do we need to improve the stability here? Under certain conditions, do we need to change some of the timing of the circuit? And that allows us to further evaluate sort of the dynamic nature of a power device as it's being used, and look at both failure states and design improvements to improve the efficiency under use case circumstances. All right, so one of the last couple of things I wanted to mention here is the importance of ripple measurements, especially when you're talking about ripple on these high voltage kind of measurements, high voltage DC measurements. The voltage and current ripple on these DC link devices at high voltage really affects the long-term life of that DC link capacitor, affects and can have a big effect on conductive emissions and harmonic measurements as well. So sometimes we need to directly monitor that ripple and analyze and characterize that as well. So this is where one of those other probes we talked about, the power rail probe, can become super important. So it can be a difficult measurement to measure the small voltage ripple and the noise event, sort of the noise effects riding on this power because of the high common mode or the high voltage riding on top of it that this noise is on top of, right? So we can use a power rail probe like this. This gives you plenty of bandwidth, so you can have up to 4 gigahertz of bandwidth with a device like this. This one has an offset range of up to 24 volts, and then you can really get a dynamic measurement range down to plus or minus 600 millivolts. So great way to then connect that to a high resolution oscilloscope with low noise that gives you a great look at whatever ripple and noise is coming through on that signal, and from there you can more accurately determine reliability, lifetime issues, changes you might need to make to that circuit to really optimize it further. So a great way to get high signal fidelity on the ripple on power lines in a configuration like this using power rail probe. And when we talk about, again, high resolution scopes as sort of the backbone of these measurements, having 12-bit oscilloscopes is really important here because it allows you to really see through uh, a lot of those, uh, some of those noise artifacts. It allows you to really visualize uh, the uh, the changes in the ripple measurements and in different effects that you might see. So you can more accurately see the the signals, the ripple and noise effects within that signal by really getting rid of some of the noise that might otherwise have been created by your test system. So combination of the low noise front end here, the gain accuracy, the isolation, and the ENOB is really the effective number of bits, the measurement precision of the scope become important aspects. All right, so to summarize, you know, we know power applications are really driving efficiency requirements. We need more efficient power. We need to be able to move power around. We need to be able to store it and use it. And whether we're using wide bandgap semiconductors or other new materials and new systems to do that, being able to accurately measure and improve the efficiency is of critical importance. And that drives the need for higher bandwidth measurements, higher resolution measurements with your oscilloscope or other measurement system. And a number of tests that we've talked through today that can help you do that, including dual pulse test, double pulse test, which uses a number of power supplies, probes, an oscilloscope, and some sort of a pulse generator. Emissions and harmonics measurements, as well as power analysis measurements, ripple measurements, you can make directly on the oscilloscope with the correct probing. Overall efficiency measurements, you can build test systems for out of a number of benchtop instrumentation, loads and power supplies and multimeters. You can look at the Bode plot of the loop response time there. That gives you the ability to optimize and optimize loop response and look at the phase margin. That you can do with an oscilloscope and a generator. And then load step response, which requires a combination of a load and a measurement toolkit, but again, allows you to further optimize. And in many ways, these measurements are interrelated, right? As changes in the Bode plot and the load step response result in emissions and harmonics, the other changes can affect efficiency directly. So really interrelated measurement techniques, but really all allow you to, with the right toolkit, allow you to improve your resolution, accuracy, bandwidth, and with the right probes and connections, can be a powerful tool set for these types of power measurements. All right, so just to kind of finish off, wanted to share with everyone, so one of our newest power supplies from SIGLENT, and we didn't talk too much about power supplies today because we talked about kind of measurement techniques around them. But in many of these systems, we use an instrument like this to deliver power. And so now you have the ability to get up to 200 volts, up to 50 amps in a single box, so up to 1500 watts. You have a nice broad power delivery envelope there you see on the right from the two models, and you can build them up into a larger system up to 7500 watts in parallel. And just to kind of finish off, right, this is all about how we can improve our power electronic systems. And if we can't measure it, we can't improve it. So finding better ways, techniques, tools, implementations that allow us to be more accurate with our measurement, allow us to find new ways to improve the efficiency of these systems and the systems overall. And that's really the end today. So there's obviously SIGLENT provides a variety of benchtop equipment that can help you with a variety of these needs. Hopefully you learned something about power electronic techniques and measurements we can make today, and hopefully you find that valuable in the future. Thanks again for joining us. Appreciate your time, and we'll move into a Q&A session. Thank you.
Thanks, Chris, for that great presentation. I know I learned a lot about doing measurements and characterizing today's modern power electronics. So I see we already have several good questions, but I just want to tell our audience that there's still time to submit questions if you'd like to. So Chris, you ready to answer some questions?
Absolutely.
Okay. So sometimes when you change power density in a circuit board, it can impact the threshold of EMC compliance standards, and sometimes you can even cross the standard level and produce some EMI problems. How do you mitigate that?
Yeah, I think depending upon exactly how you're seeing it and what it is, obviously EMI mitigation is pretty challenging, right? I think